recording a quick video on permutation, A/B testing, and conditional probability, which is all stuff that's kind of shoehorned into like the last week of discussion. So you guys didn't get too much of a chance to practice with it, but hopefully this video clears some stuff up for you. Sorry it's getting out so late, but if you do manage to catch this before you actually take your final, then I hope it helps you out a little bit. So okay, let's just get started. So we have A/B testing is essentially like you use it with categorical distributions, distributions, and then it's pretty similar to like hypothesis testing, where like you have your null alternative hypotheses, and then you use permutation testing to like come up with your conclusion. So the example that I'm going to go over like in a little bit after this is the distribution of birth weights between smoker and non-smoker mothers. So if we have like our axes here, let's say this blue color is smokers, and then this red one is non-smokers. We're going to prove that there's like some difference, I guess, in the distribution of birth weights between smokers and non-smokers. So non-smokers generally have a higher birth weight, and then smokers generally have a lower one. So it's possible that like maybe if you just see a sample, like a sample from these two distributions, like you're not sure if they are actually from different distributions. It's possible, like, okay, like maybe you just got a weird sample and like there's actually like an overlying distribution, you know, that like encompasses both of them, but like you can't know without knowing the entire population. So so we're going to be doing that in an IPython notebook later, but it's just basically like, can we prove prove that it's statistically significant. That there's a distribution, a difference in the distributions of smoker and non-smoker birth weights. Is basically like the question that we're trying to answer with A/B testing. Otherwise, we also have our permutation testing. So this one's it's not like confusing, but I guess it's just like the word like testing in it is like, it feels kind of like a misnomer, because I feel like you'd expect it to be kind of like hypothesis testing or A/B testing, where you're like, oh, like I'm trying to prove or disprove some like hypothesis that we're making, but it's actually probably more similar to like, I guess like the analogy that I would draw is closer to like the bootstrap for confidence intervals, in which it's like a method used in A/B testing. So it's like not really necessarily like a test in and in and of itself. It's more like used in conjunction with A/B testing, so not really a standalone test. So what permutation testing is, basically like you have like these two distributions, but you only see it in like one sample, right? So like if we have our table, and let's say birth weight, or no, smoker status, and then birth weight. So this, like, birth weight could be like true, true, false, true. And then smoker, oh sorry, wrong column. So true, true, false, true, false. And then birth weight would be something like 120, like 110, 95, 98, like 105. So if you have like a table that looks kind of like this, then permutation testing basically means that you shuffle one of the columns, because like it shouldn't matter if you shuffle them if they're in the same distribution, right? Because if they're both drawn from this green distribution, same. Or that would be like your null. So if they were both drawn from the same distribution, it wouldn't really matter if you shuffled like the birth weights or the smoker status, right? However, if they are in these different, like maybe they're like intersecting, but like these different distributions, then that would also leave like some, I guess, like statistically significant like result. So you shuffle the columns and then calculate test statistic of your the test statistic like of your table, I guess. So possible test statistics here, the first one that comes to mind definitely is total variation distance. Is like you always use that with categorical stuff. So that would definitely be like the first, I guess, like test statistic or example of a test statistic that comes in mind. For this example, we're going to be using the absolute difference of means. Yeah, so that's what A/B testing and permutation testing is, I guess. It's just basically saying, like, if we have two distributions, or like we think there might be two different distributions, but we're not sure, like that's what A/B testing is trying to prove. So I'm basically following the same example from the textbook, but I kind of like pared it down a lot, I think, because like the function that they used was like really, really big. So here we go. I'm also going to put a link to this in like the description. So check that out if you want to look at it, but I'm just going to restart and clear output. Okay. Okay, so here I read in just like the straight up CSV, and that's this first table, and then the second table here is just like me selecting, because this includes gestational days, maternal age, height, weight, like I don't really care about them, so I just selected out maternal smoker status and then the birth weights like from these mothers. And then here, this next one, I grouped maternal smoker status, so like false or true, and then I took the mean of all the birth weights. So here you can see if the mother is not a smoker, like the birth weight is higher than if she was a smoker. But again, that's like, we don't know if that's just our sample or if it's just like some like weird thing happened. So that's what we're going to test later. And then you can also see here is the birth weight of smoker mothers, and the birth weight of non-smoker mothers is this one, and like they both have like pretty similar shape, kind of like this, but as you can see, like this one is centered more around like this like mean, I guess, so it's like 115 maybe, and then this one is centered a lot higher, which is like around 120 or like maybe even a little higher than that. So we're just gonna compare these two distributions. This one, okay, so step one, we're doing like the permutation testing part. Or actually, okay, before that, I'll just go over my null and alternative. So the distribution of birth weights are the same for smoker and non-smoker mothers. And then your alternative is that they're not the same. And then we're also going to define a direction here, which is that smoker mothers have a smaller birth weight. Or actually, no, sorry. Our test statistic does not do that. So, okay, the distributions are not the same. So here's step one. We shuffle one of the columns, just permutation testing. So here you can kind of see, like I just did this like weird, if you do dot sample without calling anything in it, it will just like it'll have the same like numbers, I guess, but it'll just be shuffled. So you can see if I like run this a few times, like this table will be different every time. And then like right under that, I just defined a function that would shuffle it for us, because like later I'm just going to be putting into a bigger function, so it'll be a lot easier to do that. So again, like both of them shuffle every time I rerun the cell. Okay, so then the next one, we want to calculate the test statistic for the shuffled table. So the first one, or like first here, I'm showing you like where, like what the means look like after I shuffled it. And you can tell that like, oh, okay, they're like a lot closer together now versus like before they were like almost 10, I think, I don't really know what the units were. They're like almost 10 apart versus here they're almost the same. And then here, our test statistic, the absolute difference. Yeah, so here you see I took the absolute and I took the difference between these two, and then these square indexing, like don't really like worry about it. It's just kind of like I was too lazy to write dot column dot item. And then again I wrote a function to do the absolute difference, and then here I was just making sure like, okay, they look the same. So now like after we get a function to shuffle the column, and then we have our function to calculate our test statistic, and then we're ready to actually do our permutation test. So here again, like this whole simulation structure hopefully is very familiar to you by now. We have our empty array to put all of our absolute differences in, like our test statistics in, and then here is where like we do like 500 different shuffles, and each time we're going to calculate the absolute difference of the shuffled table, and then it'll return our test results. So let's just run it and see what we get. Okay, so this looks pretty similar to the table in the textbook. So you can see like since we did an absolute value, you can kind of tell like it's a one tail. If we didn't do absolute value, then like it would have been probably two-tailed with like some negative values, but we just did one. So here we do with column, differences, test results, and then I just made some bins. So now we have to see, we just have to calculate our p-value for our original table. So here, like our original difference of means was again like almost 10, and you can see like that's way far off this distribution. That's like all the way out here. So the p-value of it is actually 0. So then we can conclude that we reject the null hypothesis. Move up a little. There is a statistically significant difference between the birth weights of smoker and non-smoker mothers. Okay. Cool. So that is the permutation testing, A/B testing part of the video. Again, I'm going to put the CSV that I kind of ripped from the textbook, as well as like a link to the download file of this IPython notebook in the description so you can check it out. And then now I'm going to talk about conditional probability. So back to the notes. Conditional probability, which is basically, in this class, it's just Bayes' rule. I don't know rule. Okay, so I guess here what the conditional part means, it's basically that you're updating your probability space. So what that means, it's like you're saying you want to calculate the probability of some event B happening given that A happening. So that's the notation, is probability of B given that you know A happened. So I'll just write out the formula for you to see. I'll use different colors because it's always a good time. So the probability that B given A is the probability of B and A happening over the probability of B and A plus the probability of B and not A, or A and not B, sorry. So what this is saying is basically like, if we know that A happened, then we're basically going to restrict our probability space to all of the, I guess, like all of the situations in which A already happened. So here, restrict probability space to possibilities that A happened. Okay, cool. So now that we have like this like formula, I guess, we can try doing like some practice problem. I'll draw some trees. I think that'll, like, the tree helps a lot, I think. So here, let's have our example. I think this is one of the discussion examples, where let's say we have sophomores. Okay, let's say we have like 60 sophomores. And of those 60 sophomores, 20 have declared. And then let's say we have 100 juniors. Of those, 60 have declared. Okay, so with this, let's go to our first question, which would be, let's just say pick a student at random. What's the probability that they're a sophomore? So that would just be, you know, like 60 over 160, right? Because, you know, like there's 160 total students. We didn't really use any of this information. We just picked a student at random. But what if we said, again, pick a student at random. But if we know, like they tell us they have declared. So this is like the conditional probability, like the condition is that they have declared. So I guess expanding on that, we would say like, okay, like 20 have declared out of 60, which means 40 have not. Then here 40 have not. Like 40 juniors have not. So I guess like if we know that this person, the student, has declared, then like we don't really care about these students, I guess, who haven't declared. We're only going to be looking at these two groups of students, which are sophomores who have declared and then juniors who have declared. So here we would say like, again, if you go back to like this formula up here, like this would be the probability that they're a sophomore given that they have declared. So that would be the probability, or so that I guess like there are 20 sophomores who have declared, so that's be 20, and then divided by your full divided by your full probability space, there's 80 students total who have declared. So this is your probability for that one. I'm going to do a quick example. Oops. Oh my goodness. Okay, so I'm going to do a quick example off the review slides. Sorry. File. Okay. So this Fall 2016 decisions question. So in a population, 85% of the people are in Class A, the remaining 50% are in Class B. This is not the right one. Okay, lie detection. Lie detector is shown to be 80% reliable when the person is guilty, 95% when the person is innocent. If a suspect is chosen from a group of suspects where only 1% have ever committed a crime, and the test indicates that this person is guilty, what's the probability that they're innocent? So you could use the, I guess like the formula that we gave before, but I think like a nicer way to do it is probably like with trees. So let's like draw this out. So there's two branches here, right? One is if they actually committed a crime, and then one is like what the test says. So someone brought up in one of my discussions, which I thought was like pretty good, is that you could think about the order in terms of like the order in which events happen. So like the first thing that happened is that they actually commit a crime, and then the next thing that happens is that they like take the lie detector test. So let's see. So let's start with this part. So there's like a 1% chance that they committed a crime. and then 99 that they did not. And then here is like the results of their lie detector test. So when the person is guilty, 80% accurate, they are guilty. So then there's 20% wrong, not guilty. And then here is 95% reliable when the person is innocent, so 95% accurate. So the lie detector test would say not guilty. And then 5% wrong, and it would say guilty, which is like a false positive, right? So we're here saying the test indicates that a person is guilty, so that would be this, and then this. What's the probability that they are innocent? So out of these two, it would be like, what's the probability of this? So here you would just kind of like go down this tree. So the probability that they committed a crime and they are guilty is 1.01 times 80, or 0.8. And then this one would be 0.99 times 0.05. So then the full probability would just be 0.99 times 0.05 over, 0.99 times 0.05 plus would be your full probability. And then that's also how you build your trees. Okay, so that's it for permutation testing, A/B testing, and conditional probability. I hope that this video helped you, and then if you have any questions, feel free to email me, leave a follow-up on Piazza or anything like that, and good luck studying.